In this section, we're going to look at several other groups of identities or formulas, and we're going to work with them. The first group is called double angle formulas, and here they are. It's a sine of 2 times some angle, you see, and cosine of 2 times some angle, tangent of 2 times some angle. Notice that cosine 2 times u has 3 different versions we can choose from. And that's rather interesting, because in some situations we'll want one of these and not the other two, as we'll see in just a moment. Now, all of these can be derived from, well, the second two can easily be derived from the first one, so you really only need to remember one, and then you can derive the other two as you need them. And the way they're derived is like this. You think of cosine squared u minus sine squared u. All right, that one, if we remember that one, then we can replace this with, now using the Pythagorean identity, we can think of this as 1 minus cosine squared, you see. And 1 minus cosine squared, with a minus sign right here, that's minus 1 plus cosine squared. Cosine squared, that's 2 cosine squared minus 1. You see, we've just derived this one from that one by using that little replacement. And if we use the replacement on cosine squared, we would get the other one. Okay, so that's the idea. At any rate, it's just the notion of looking at them, recognizing them, and then using them in certain situations, and then they will become familiar. The important thing here, I think, is not to become intimidated by all of this stuff. These are just formulas, you know, and you've used formulas many, many times in the past. And so just kind of refer to them and make use of them without trying to memorize anything. If anything is to be remembered, then the memory will come by great use, and not by sitting down and going through a memorization process. Okay, consider this problem. Now suppose we're talking about x in the interval from 0 to 2 pi, and we want to find the zeros of this function. Now the zeros, the place where the graph crosses the x-axis, zeros of factors, all of that comes into play here. Now, for the zeros of this function, we just set h of x equal to 0 and solve this. And to solve it, since we see that we have a double angle situation here, we refer to our list of double angle formulas. Now, one thing we need to do here is choose rather wisely the version of cosine 2x that we want. Remember that there are 3 versions. And if we look at the 3 versions and we look at what we have here, we might decide, well, you know, the prudent thing to do if we're going to be finding factors of this expression, and that's what we're trying to do here, is to rewrite this using only one ratio. And we'd like that ratio to correspond with this. So let's go back and choose the one involving only cosine. So we'd slide back over here. No, that involves cosine and sine. Oh, this one involves only cosine. That one involves only sine. Let's use this one. You see, that's how you make the decision about this kind of stuff. All right, so we're going to use this in place of cosine 2x. And so I'm going to write 0 equals. Now, instead of cosine 2x, I can use the formula 2 cosine squared x minus 1. All right, and then this is minus cosine x. And now we have an expression which is quadratic in form, so we'll rewrite it in the normal way, that is 2 cosine squared x, then minus cosine x, and then minus 1. And now we want to factor 2 cosine x, and then times cosine x to give that first term. And then the signs are different, and I think the way it goes is plus 1 minus 1. Let's verify the middle term. We have 2 cosine x minus times minus 1 is minus 2 cosine x, plus cosine x is minus 1 cosine x. That's the middle term, so this is the correct factored form. Now we want the zeros of the 2 factors, so we set them equal to 0 and solve them. That is, we're asking ourselves what value of x will cause 2 cosine x plus 1 to be equal to 0. And we go through that little process. Now recall that we'll kick the 1 to the other side and divide by 2. And I'm running out of room at the bottom of the board here, so I'm going to consolidate 2 steps. This is minus 1/2. And now we're going to evaluate this. Let's go over and solve this one right quick. We have cosine x, then minus 1 equals 0, or cosine x equals 1. Okay, for this one, well, let's see, cosine x is negative 1/2. Well, I need some more information here. I need to go to that 1, 2, the square root of 3. I'm talking about cosine, so it's adjacent over hypotenuse. Oh, that's this angle. It's 60 degrees or pi over 3. So we're thinking pi over 3. Now we go to the idea of the coordinate plane, and we're talking about cosine here. Now cosine is positive in these two quadrants and negative in these two, so we're talking about a reference angle of pi over 3 that appears in these two quadrants. So we're talking pi over 3 in this quadrant, pi over 3 in this quadrant. All right, and now we're just asking ourselves what is this angle, and then what is this angle? See, that's all we're after. All right, if this is a reference angle of pi over 3, this is 3 pi over 3 at pi. It's 3 pi over 3 minus 1 pi over 3. That's 2 pi over 3. So this is an angle of 2 pi over 3. X then, I'll put them down here. X is 2 pi over 3. And then this one is 2 pi over 3, 3 pi over 3, 4 pi over 3. So that angle is 4 pi over 3. Now, for the other one, for the cosine x is equal to 1, well, gee, the cosine curve is at the top of its amplitude at the beginning of the cycle and at the end of the cycle. So x needs to either be 0 or 2 pi. Now, let's look back at our restrictions up here. Now, I breezed through this real quick, and I should have emphasized it a little more. X is between 0 and 2 pi, but notice that this says x is strictly less than 2 pi. So we can't use 2 pi in our list of values for x, but we can use 0. So adding to our list of solutions here, we would include 0. So these are then the 3 zeros for our function as requested. Here's another one. Now again, let's talk about finding the zeros of the function and using the techniques that we're talking about here. Also, we're restricting the value of t for values between 0 and 2 pi, but not including 2 pi. All right, so we begin by going 0 equals sine 4t and so on. Now, gee, I'm looking at that 4t and I'm wondering how in the world, we don't have a formula for that, but here's what we do. We let a letter like n stand in for 2t. Now, if we do that, then we can think of this as sine 2 times n. You see, n is 2t, so this can be thought of as 2 times 2t, but 2t is n, so it's 2 times n. And this is 2 sine, well, if n is 2t, then that's n. You see, so that's the idea. Now, we'll back substitute in just a minute, but looking at it like this allows us to use our double angle formula. So this becomes, now let's see, I'm having to refer back to it. I'm just going to look back over there and see what it is. And that's what you're going to have to do too. When you first use these, just refer back to some kind of chart or some place in your book and just write the formula down. It's 2 times sine times cosine. So it's sine n cosine n plus 2 sine n. Now I wonder if I can get some mileage out of the algebra within this before I even go back and substitute for the 2t and the n business. Now I'm noticing here that I have sine n here, excuse me, I have 2 sine n here, and I have 2 sine n over here. So I can actually factor 2 sine n from both of those terms. So 2 sine n times cosine n plus 1. You see, when I pull 2 sine n out of this term, I'm left with cosine n. When I pull 2 sine n out of this term, I'm left with simply 1. Oh wow, that's convenient. Now, maybe it's time at this point for us to go back and do the back substitution and put the double angle idea back in here. Let's do that. We have 0 equals 2 sine 2t times cosine 2t plus 1. All right, now we have another substitution thing to go through. So 0 equals 2. Now sine 2t, again we're using the double angle formula for sine. So it's 2 sine cosine. Remember, it's sine t cosine t. And then this business is cosine 2t plus 1. Wow. You know, when I finish with all of this, when I manipulate this down, I sure would like to have a string of factors here that I can just look at. And I want those factors in the simplest form possible. So when I go and choose the cosine 2t replacement, the double angle replacement here, I'm going to try to look for something that will eliminate the 1 if I can. And it probably doesn't make any difference. We can manipulate our way out of it probably if we choose one of the other two. But if I have my choices, and I do, then I'd like to cause the 1 to go out. So let's slide back over here. Come on back over here with me and let's look at these 3. So if I'm looking at these 3, I have a 1 involved here and a minus 1 involved here. So I'm going to use this version of the double angle for cosine. All right, so here we go. Now, the letter involved over there is t, so it'll be 2 cosine squared t minus 1. Let's go over there. 2 cosine squared t minus 1 is the identity for this, or the formula, and then this plus 1 comes down. And then the 1's go out, and that's what we wanted to have happen here. So those are out of here. So now we have all of this business. Let's just clean this up. Now I'm going to just consolidate right here in the interest of time and space. I have 2 times 2 times 2. That's 8. And I have sine t cosine squared t. How many factors of cosine t do I have? I have 2 of them here, another one here. So this is cosine cubed t. Okay, now I have a consolidated situation which I can deal with in evaluating. Now, the idea is that I want the value of t that will cause each factor to become 0. Is there any value of t that will cause 8 to become 0? No. 8's just dead weight here. We can just kind of throw it out. Now, sine t equals 0. See, I'm really thinking in terms of, and I need a little space here. Let me back up over here and make sure we understand what we're trying to do. In this factored form, we are trying to find the values of t that will cause each factor to become 0. And what's down there is 0 equals 8 sine t cosine cubed t. Okay, we said that this makes no difference. And now we're looking for the values of t that'll make sine t equal to 0, and the values of t that'll cause cosine cubed t to be equal to 0. So we're solving these two. And both of them are fairly easy. The sine of what angle is equal to 0? Well, we're just thinking of the sine curve, and where on the sine curve do we have x-intercepts? Well, let's see. We have x-intercepts, and without even drawing it at some point, we ought to be able to imagine how that sine curve goes. It starts at an intercept. It starts at 0. It goes to the top of the amplitude and back through 0. You see, so it starts at 0, goes to the top of the amplitude, back through 0 at pi, bottom of the amplitude, and then back to 0. But that last 0 occurs at 2 pi, and we're disallowing that value. Okay, so 0 and pi for this. All right, now, what about cosine cubed t? Now, understand that, that in solving this is cosine t all cubed, so I can sort of take the cube root on both sides. So this is equivalent to having cosine t equals 0. Okay, now we want the angles which have a cosine. Cosine of what angles would be 0? Well, think about the cosine curve. The cosine curve starts at the top of the amplitude, then we have a 0 at pi over 2, and then we go to the bottom of the amplitude at pi, and then we're back up at a 0 at 3 pi over 2. Now, if you're not recalling these things as I am talking about them, then it's worthwhile to construct the graph of the cosine curve and actually look for these actively on that curve. So anyway, we have solutions, we think, at 0, pi, pi over 2, and 3 pi over 2. Let's use the calculator to verify those solutions.
The equation has already been entered, and I have made some window settings. Negative 0.5 for the x minimum, 2 pi for x max. The x scale should be set so that we can see our solution points easily. All of our solution points are multiples of pi over 2, so I'm going to set the scale at pi divided by 2, and the y minimum negative 3, y max 3, and here's what the graph looks like. I want you to notice how the graph appears to flatten right here where it goes through the x-axis, and here again as it goes through the x-axis. So it's maybe a little difficult to see that these are indeed solution points. We'll do something about that in just a moment, but we know here at 0 that's a solution point, so that's verified. Our x scale was pi over 2, so this is a distance of pi over 2, so that point is pi over 2. That was another of our solution points. This is another distance of pi over 2, so this whole distance is 2 pi over 2, or simply pi. So there's the position for pi. And here's another pi over 2, so we have 3 pi over 2 for that point. And notice we have a crossing here at 2 pi, but that was out of our domain and doesn't really count here. All right, to take a little bit closer view of this point of intersection, what we can do is reset our y maximum and minimum, and we're going to do that and sort of magnify this portion of the coordinate plane. We're just going to come in tight like this, and it'll cause the graph to look a little more vertical in that region. Here's what I'm talking about. I'm thinking of a y minimum at negative 0.5 and a max of 0.5. And now notice that the graph does not lay down or get flat as much at those points. And that's just a technique that you can use from time to time when you fall into a dilemma like this.
In this problem, we're told that the tangent of an angle u is 1/2, and we're also told that u is between pi and 3 pi over 2. Now, this information simply puts the angle into the third quadrant. So we have a third quadrant angle. You see, it's this angle, which has a reference angle in here, which causes a tangent of 1/2 to emerge. So we have a reference triangle like this, and we can think of, let's see, opposite over adjacent. So this would be 1 and that would be 2, but since we're in the third quadrant, they're both actually negative. Now, let's calculate from this information. Let's calculate sine 2u, cosine 2u, and tangent 2u. Well, we're going to use our formulas for each of these, but it's going to be handy for us to find the value of this hypotenuse. Now, it's c squared, you see, is a squared plus b squared. So we're talking about an a squared and b squared of negative 2 squared, negative 1 squared. That's 4, that's 1. So 5, c squared is 5, c then is the square root of 5. So square root of 5 for this. Now, for sine 2u, I refer back to the formula over there, and the double angle formula. So it's 2 sine u cosine u. And now I'm just referring to the triangle. So I have 2 sine u, from the perspective of this side, opposite over hypotenuse, is negative 1 over the square root of 5. And then for cosine, it is adjacent over hypotenuse, so that's negative 2 over the square root of 5. And so I just evaluate this. With 2 minus signs and factors, I know we're going to get a positive result. So we have 2 times 2, 4, over the square root of 25. So this becomes 4/5. Now, for cosine 2u, I have 3 options. I can choose one of 3 double angle formulas here to replace. I think I'll choose the one that has only one ratio involved in it, so I don't have to evaluate more than one ratio. Well, okay, let's do that. I'm going to just look back over there. I'm seeing the one involving, let's say sine. It is 1 minus 2 sine squared u. All right, and away we go. Now, we understand this, excuse me, to mean sine u all squared. That's the way we need to think about it when we plug in, because it's 1 minus 2 times, now what is sine u? Well, again, we look back over here, and the sine of this angle opposite over hypotenuse. So it's negative 1 over root 5. So negative 1 over the square root of 5, and all of this is squared. And now it's a matter of evaluating. And we can just about think our way through it. When we square the negative, it's going to be positive. When we square the 1, it's going to be 1. And when we square the square root of 5, it's going to be 5. So this is just 1/5. Now, 1/5 times 2 is 2/5. You see, so this is 1 minus 2/5. I'll write that down. So 5/5 minus 2/5 is 3/5. So 3/5 for cosine 2u. Now for tangent 2u, same idea. We just go to the formula, and I'm looking back over there. I know it's a fraction. 2 tangent u over binomial 1 minus tangent squared u. And let's see, 2 tangent u. So 2. Now tangent u was given at the get-go of the problem. So it was 1/2. So this is 2 times 1/2. And over 1 minus, now this is just 1/2 squared. You see, because tangent u was given as 1/2. So let's see, this is just 1 in the numerator. And in the denominator we have 1/2 squared is 1/4. 1 minus 1/4 is 3/4. And 1 divided by 3/4 is 1 times 4/3, or simply 4/3. So 4/3 then for the tangent of 2u.